Good afternoon, everybody. Thank you for being here once again. This is another session of our QRC seminar. And today we have Professor Tracy Northup, which is a researcher that I know since long ago. And she's been doing very cool stuff in the University of Innsbruck, where she's a professor at the Institute for Experimental Physics there at the University of Innsbruck in Austria. And her research explores quantum interfaces between light and matter. She focuses on trapped ion and cavity-based interfaces for quantum networks and quantum optomechanics, right? So this is one of these nice examples of where we will learn physics about light and matter. So we're very happy to have you here, Tracy. Thank you so much for your time and availability and being here with us remotely. And please, be aware that you're welcome to visit us in person also soon, whenever you wish. Thank you so much. You can go ahead.
Leandro, thank you for the introduction and also for the invitation. And yeah, I would love to visit in person. So it didn't work out this time, but it's great to be able to share with you our research online and to have this opportunity. So I'd like to tell you about work that we're doing in my group about quantum interfaces. Let me briefly show you where we are. So where Innsbruck is the largest city in the Alps, sort of in a north-south valley here. It's not snowy right now, but in the winter, this is what it looks like. And we're kind of between these two mountain ranges. It's a beautiful place to do quantum physics. So I also encourage you to think about visiting sometime. Big picture I want to think about today is how we can make connections between different kinds of quantum systems. And as we now slowly start to travel again, these are the kind of devices that we bring around to make connections between kind of man-made systems, right? This is a kind of a classical interface solving a man-made problem because we decided that in different countries we were going to use different kinds of standards. And so we could solve that. You know, we don't need this kind of interface if we would all agree on one standard. But in contrast, I would argue that quantum interfaces, the problem we want to look at today, is really a fundamental problem. It's not a problem we could just wish away by finding a single solution. And the reason I want to argue that is because we have really a beautiful diversity of different kinds of quantum systems that we get to explore right now in this field. So for example, in quantum computation, people focus on many systems, among which are trapped ions or superconducting qubits. And perhaps it will turn out that those are the best platforms for computation, but it may be that there's another platform such as neutral atoms that's more suited for quantum simulation, for quantum sensing, maybe something like nitrogen vacancy centers, or maybe the kind of levitated systems, for example, that Renee is working with at your center, and quantum communication. Of course, people think about photons. So we have, again, this multiplicity of different systems. We don't expect that any single one of them will be the one answer for quantum technologies. And we also expect that they're not going to simply operate separately in their own domains. So we anticipate that connecting these platforms will enable fundamentally new capabilities for quantum technologies and for quantum applications. And so that perspective within Europe and worldwide is motivating efforts to harness superposition and entanglement for quantum technologies. Here's kind of a picture of the roadmap in Europe that people came up with now more than 5 years ago, and kind of mapping out now until 2035, a vision that includes clocks and sensors and quantum simulators. And the kind of work that we're particularly interested in, which is like quantum internet, quantum communication. And so this is kind of the basis for a big initiative in Europe currently going on over 10 years. But of course, worldwide, this is also a very, there's many different national and international initiatives to kind of understand how we can build these quantum technologies. However, I do want to emphasize that this is a talk not simply about applications, but really about underlying fundamental physics. And this is what I find so beautiful about quantum interfaces and light matter interfaces at the level of single atoms and single photons, that on one hand, we get to really look at very fundamental interactions of quantum mechanical systems and ask, and try to understand the basic physics here. But on the other hand, that there's really this important role that we expect these interfaces to play for future technologies. So that's why I'm excited about this field. I hope I can share with you today a little bit of the excitement that we're having in exploring it. And what I want to tell you about are two different kinds of quantum interfaces that we are working with in my research group. And then I want to turn to one of those, looking at how we've recently been able to link together two different ions in different laboratories in a collaboration with a colleague of mine here in Innsbruck. And then in the second part, I will move on to the second example and tell you about how we would like to move with quantum optomechanical systems towards macroscopic quantum states of motion. So let me start by giving you the overview of these two different examples that I want to focus on today. The first example is looking at a quantum internet, the idea of being able to generate large-scale connections that allow us to transfer quantum states over long distances. And so this is a vision that involves quantum nodes at individual locations, where we should picture that there's local quantum computation, simulation, and sensing that can go on. And what we'd like to do is link those quantum nodes via quantum channels, that is, by distributing entangled states. More generally, we'd like to be able to distribute any kind of quantum state, and that includes then the distribution of entanglement and being able to preserve entangled states over long distances. And so the large scale question for these quantum networks is to say, how can we distribute entanglement efficiently and with high fidelity over long distances? And this is a slide, as you see in the upper right-hand corner, from a consortium called the Quantum Internet Alliance. It's a European project that I'm part of with many other research groups. And so this is kind of a large-scale vision for that consortium, and not only the work in my group. So on one hand, I'd like to look at this question of a quantum internet today. And on the other hand, I want to talk about quantum optomechanics. And so as we know, quantum mechanics describes the world of atoms. When I took quantum mechanics, I had an earlier version of this textbook, but it still had a live cat on the front cover and a dead cat on the back cover, kind of reminding us or asking us to think about the strangeness of this idea of Schrodinger's cat. And so we certainly expect that the laws of quantum mechanics describe the macroscopic object around us, but our experimental experience is with worlds of atoms and photons. And so can we observe the kind of superposition and entanglement that we've now been able to generate and at small scales with atoms and ions and photons? Can we observe that now at large scales? And here in particular, we're going to look at the center of mass motion of a macroscopic object. And for us, light is going to be a kind of a knob for quantum control that's going to enable us to have the same kind of control over the states in the long term we hope that we do have over atomic and photonic systems. Okay, so those are the two systems that I want to look at today. And then I want to describe two ingredients that we're going to use that will be shared across those two systems. And so one is looking at ion traps. And so we're using here what's known as a linear Paul trap. And so I just want to show you kind of a lot of different pictures of these linear Paul traps to show you that there's a diverse range of different kinds of setups that can be used to trap individual ions. And the big picture is that we're using electromagnetic fields to provide a confining potential for charged particles. So I'm not going to go into the details of ion trapping here, but what you should picture is that we're applying radio frequency to some electrodes that's providing a very deep confining potential that allows us to trap both single atomic ions and as well as strings of atomic ions, but also charged particles that are a lot heavier, such as these nanoparticles I'll talk about in the second part of the talk. And the second ingredient is looking at optical cavities. And so just in the same way that an ion trap is a trap for ions or for charged particles, an optical cavity is something you can think about as a trap for light, for single photons. And so if you have two highly reflective mirrors that are facing one another, you can think of a single photon bouncing back and forth hundreds of thousands of times between these mirrors before it escapes. And what we do is we confine the interaction, using these mirrors, we can confine the interaction between that electric field and a single particle to a very small mode volume. And so that's something that's been pursued now for some decades, starting with pioneering experiments, for example, from Serge Haroche's group, back looking at microwaves and Rydberg atoms, the basis for the Nobel Prize work in his group. In this case, interestingly, even though we think about photons as something that travel, here the cavities are confining the photons. And so what we should picture here is that these are atoms that are traversing a cavity, and the photons are the things that are trapped thanks to highly reflective mirrors. Later experiments, such as these here, shown here by Jeff Kimball, took these experiments from the microwave domain into the optical domain. In this case, then working with sort of atoms in their usual lower lying states. And more recently, there have been many extensions to solid state systems, including superconducting qubits coupled to microwave resonators, as well as nitrogen vacancy centers and as quantum dots coupled to optical resonators. So this is a very broad tool, and these are the two ingredients that I want to think about today. On one hand, traps for charged particles, and on the other hand, cavities as traps for light. So with those two platforms or two overarching themes and goals and two ingredients, I want to go on and go into more detail on the first one, this concept of a quantum interface. I do also want to mention, as Leander asked at the beginning, you're welcome to interrupt me at any time with questions, and please just let me know if you have any. So moving on to the first one of these examples, back to this idea of a quantum internet. Let's talk about where we are, what the state of the art is right now worldwide. And so, there have been a handful of experiments with here, maybe couple more platforms than the one I'm listing here, but not so many. Platforms like ions, neutral atoms, nitrogen vacancy centers, quantum dots, superconducting qubits, where we can link two different systems that are physically separated over some kind of photonic channel. So you can think of these as platforms for quantum information processing. The record distance of linking together kind of two of these single systems is just over a kilometer, although that's sort of a physical distance. So there's been more recently, for example, from Harold Weinberger's group, there's been experiments of more like, I think, 33 kilometers, where that's a fiber coil between the two systems. But kind of in terms of physical distance, something like a kilometer, and the rate at which people have been able to entangle those remote systems kind of ranges from kilohertz or hertz up to kilohertz regimes. So this is kind of how fast could you generate remote entanglement, and that's the range of kind of 1 to 1,000 hertz that people are looking at. People have also been able to teleport states from one location to another. So that's again a picture of two nodes joined by a single quantum channel, but at one node you would have two quantum systems, and entanglement between two systems would allow you to, would give you a resource with which you could teleport a single state from one node to the other. Then I want to comment, so this is kind of the state of the art for two nodes that has been reached in a handful of systems, and there have been now just a few experiments with 3 nodes. For example, in John-Wayne Pound's group, 3-node entanglement of atomic ensembles that was able to be sort of verified after the fact back in 2019. And then the next year, deterministic 3-node entanglement of NV centers in Ronald Hansen's group. And even more recently, just 2 weeks ago, there was a publication about teleportation from the same group. So again, kind of even fewer systems where people have been able to link together 3 nodes. So that's a broader picture. And then, I've told you that we're focusing on ion traps. And so let me tell you about what's been done with trapped ions so far.
So Tracy, when you mean 3 nodes,
Mm-hmm.
like entanglement and teleportation as a bipartite, let's say, primitive, or what do you mean by 3 nodes? So
yeah, so there
any 2 pairs out of these 3 nodes can communicate quantumly. That's what you mean.
Yeah, so I think the 2019 work, that was like one single tripartite entangled state, but I would have to check again about that. I know that with the work from Ronald Hansen's group, right, so 3 separate nodes, and they did 2 different things there. On one hand, they generated GHZ states, so tripartite entanglement across all 3, but they also did the other thing that you mentioned, where you use the intermediate node as a gateway to generate the entanglement between the remote nodes. And that's the same thing with the teleportation. So the teleportation with the 3 nodes was to say that you could use the intermediate node to entangle the remote nodes, so that then you could teleport between 2 nodes that had no direct connection between each other.
Wow. All right, cool, thanks.
Yeah, so super from an ion trap perspective, super exciting what people have been doing with NV centers. And, so, we feel, like, well, let's see what we can do with these ion traps. What's been done so far with ion traps? These were actually the first system, the first matter qubit to be remotely entangled. Sorry. Neutral atoms were first. But this was the first matter qubit to have atom photon entanglement. And then, and then there was remote entanglement of neutral atoms. This goes back to work really in Chris Monroe's group, formerly the University of Maryland, which is where the work was carried out. Now he's at Duke University. And so this is a picture from an experiment in which they first entangled 2 ytterbium ions, each in separate ion traps, separated by a meter. And it was detection of photons. We'll go into that a little bit later. Detection of photons is able to prepare these 2 ions in different ion traps in an entangled state. And more recently, just a few years ago, the Oxford ion trapping group led by David Lucas was able to entangle strontium ions in a very similar way with even higher rates and efficiencies than had been achieved in Maryland. So until now, there's been 2 research groups so far that have entangled remote systems. And ions are really an exciting platform for this, because even though in these experiments I'm describing to you, those were entangling one ion in one place and another ion in another place, more generally, ions are a system with which it's relatively straightforward to work with registers of tens of ions. I'm showing you kind of some state-of-the-art numbers. For example, if you want to be able to individually address and manipulate ions, people have been doing things like characterizing entangled states of up to 20 ions. If you don't need to individually address each one, but you're more interested in creating global entanglement across that whole space, for example, for quantum simulation, this is an example of a paper from Chris Monroe's group, the second example, with about 53 ions. And then another wonderful thing about ions is that they have very long coherence times. They can store entanglement for a long time, and in fact, fast. So current experiments, the 2 experiments that I've shown you, have fast remote entanglement rate, and in particular in the Monroe group, it was shown that they could generate remote entanglement faster than decoherence in the individual systems. Right, how do we go from these kind of 2-node state-of-the-art experiments to this vision of a quantum internet, and in particular to experiments which are maybe just over a few meters in the same laboratory, to these kind of scales that would be on the scales of countries or continents? So we're not going to do that in this talk today, but I want to try to show you how we're trying to move this forward. We're working on a cavity-based platform. So what I'm showing you here is an experiment in my group where we're using an ion trap, and that's right there in the center of the photograph. It's tilted by 90 degrees from this little schematic that you see here. But the idea is that we apply radio frequency voltages to these blades, and that's providing the confinement for a single ion or multiple ions. Then what you see on the left and the right side of the ion trap are stainless steel cylinders that are holding highly reflective mirrors, and they're separated by about 2 centimeters. So this is our optical cavity. And here I'm also in the upper left showing you a schematic of the cavity system as well. That's showing you a standing wave picture in which the ions are confined. So next, what I want to point out is that this concept of linking an ion to a cavity, this goes back to a very well-known proposal or paper that was by Jeff Kimball called the Quantum Internet in 2008, summarizing this vision of cavity-based interfaces as a way to coherently link light and matter. I'm going to tell you today about an interface that's based on entanglement that doesn't actually require a coherent mapping. But I want to point this out that you can also imagine coherent state transfer that requires a cavity between the electronic states of the atom and the field of the cavity mode. So the physics of this interaction that I want to tell you about is driven by a Raman process. And we use that Raman process to generate single photons in our optical cavity. So I want to just outline here the sort of simplest version of the underlying atomic physics. We work with calcium ions in these experiments. So it's calcium 40. And you can picture here a 3-level system, so called lambda type system, because we have 2 ground states and an excited state. And so generally in atomic physics, in a Raman transition, people want to transfer population between 2 ground states via an excited state, but never populating the excited state. And generally that's a process with 2 laser fields that have an energy difference that matches the energy difference of the 2 ground states and a phase relationship between the laser fields. Here, we're only going to use 1 laser field. And where the other laser field would be, we're going to instead use the vacuum field of an optical cavity. So it's a little bit different than a standard Raman transition, but it can achieve the same effect of transferring population between 2 ground states, while in the ideal case, not populating an excited state. So if in this diagram, we have an atom or an ion in the left-hand ground state, this S1/2 ground state, and now we introduce a laser that's slightly detuned from the P3/2 excited state, and we couple a cavity also slightly detuned from that excited state to the second ground state. It's actually a metastable state because the lifetime of about a second. That creates now an energy difference between the laser and the cavity that matches the energy difference between the 2 ground states. And the result is that the atom can be transferred from the left-hand side to the right-hand side, where you can think of it that we pull a photon of energy out of the laser field. And that means that we have to generate a photon out of the vacuum in the cavity. And so this photon appears in the cavity mode. The ion is now in the other state. And if this were simply a coherent process, it would go back and forth like that forever. But the cavity is also partially transmissive. You can picture that, these mirrors, as you can see in this right-hand mirror in this diagram, it's possible that a photon can kind of leak out of that cavity. And so then we're able to take that cavity out, send it to somewhere, take that photon out of the cavity and send it somewhere we're interested in sending it. Finally, we can also tell the difference between which state the atom is in by using what's called fluorescence detection or quantum jumps. And so here what we're doing is we're introducing another higher excited state. This is labeled P1/2 on the left-hand side. And so we can introduce a laser that couples the S1/2 state to the P1/2 state, which is to say that if the ion is in the S1/2 state, it will then be excited repeatedly to this other state, this P1/2 state. It fluoresces millions of times a second. And so if we use a camera or a photomultiplier tube, we get a very bright signal to us that the atom is in this S1/2 state. But if the atom is in the D5/2 state, it doesn't couple to this new state at all. And so it's simply dark on our detector. And this is how we can tell the difference to perform a projective measurement that the atom is either in S or it's in D. Finally, the last tool that we have here in our toolbox is that we can actually directly couple those 2 ground states with an optical transition. This is a quadrupole transition, so it's dipole forbidden, but we do have a quadrupole transition that links these states, and it's resonant at an optical frequency that's easily accessed with a very narrow line width laser. So I've showed you how we can...
the creation of the photon in the cavity is entangled with a transition between the 2 ground states, right? Or,
so
well,
great question. Yeah.
Sorry, it's not entangled, right? You will use it for establishing entanglement. I can guess, right?
Perfect. Yeah. So what we just did here, so that's exactly the transition that I wanted to make now. Great. So what we did so far was we started with just generating a photon, but we don't have entanglement yet because this is just making a single photon. So to get entanglement, we need one more step. Because what we want to do is actually have a polarization degree of freedom here. So we want to entangle the state of the ion with the polarization of the photon. We could have an entanglement that was based on photon or no photon, but it can be more useful for long distance transmission to use polarization. So what we can do is we can take advantage of the fact that the D state actually has a manifold of Zeeman states. And so we can introduce another different state here, which I'm calling D prime. We have 6 different states to choose from, so we're just picking 2 that work well for us. So we have now two states, D and D prime, and we can drive two different Raman transitions, one to each final state. And we choose them so that the polarizations of the two transitions are orthogonal, the polarizations of the photons in the cavity. And so that means that we can start in our original state S and map ourselves to the D state and generate a horizontally polarized photon, or we can start in S and map to the D prime state and generate a vertically polarized photon. And then when we drive those two processes in parallel, we have an equal probability to generate both. So half the time we can generate DH and half the time D prime V. But more importantly, there's a phase relationship between those. So in writing down that summary, that's really expressing a quantum state that has a definite phase relation. And therefore the ion and the photon are now maximally entangled with each other. So we generate this.
Tracy, the 2D levels, are they different hyperfine levels of the metastable?
They're different Zeeman states. So we apply a magnetic field to split out.
Magnetic field, I see. Okay.
Right.
Thanks.
And they're split out by a couple of megahertz.
I see. All right. Cool. Thanks.
You're welcome. And so the cavity frequencies are the same. And so to compensate for the different magnetic field splittings, that's why the two little arrows on the left-hand side actually have different frequencies to match them. So this is an example. This is the work we did now 10 years ago when I was a postdoc in Rainer Blatt's group in Innsbruck, looking at generating these ion photon entangled states. And what we can do is then measure the ion and the photon in three different bases each to map out the density matrix that describes a joint ion photon state. And that allows us to characterize the density matrix and thereby to characterize different properties of that state. For example, the fidelity, we look at the overlap with a maximally entangled state and see that it's very highly entangled. And we also see that we can tune the relative phase and the relative amplitudes of those states and still maintain a very high fidelity. So these kind of cavity coupled entangled states have some really nice advantages for quantum networks, in particular, because we generate the entanglement through a coherent Raman process rather than through spontaneous emission, which is what's been done in other groups to use spontaneous emission. We have a lot of control over the amplitude and phase of the entanglement. We can also control the temporal wave packet of the photon that leaves the cavity. So this is a picture of sort of, if you take a histogram of the photons that come out of the cavity, what they look like. And it's describing, it's showing you that, it's kind of a funny asymmetric shape, but we actually have control over that shape if we adjust the driving laser field.
1 second, Tracy, wait. Renee,
yeah, you see there's a message.
Renee is sending messages. Davia, are you still there, Davia?
Yes, yes.
Is it possible to give everybody, all the participants, to have permission to speak? That's what Renee is asking. That would be nice. The ones logged remotely.
Yeah, but usually for the questions, we just do it through the chat box in case.
Yeah, but I always, okay, so I didn't discuss this with you, but with the person that was before you, like I always insisted on the fact that it's easier for us if you give permission to everybody for speaking, if you can.
Yes,
if not, we do the hand raising, but yeah.
Okay.
Sorry, Tracy.
No problem.
Thank you, Davia. Thanks for that.
Sure.
Renee, or do you also want to? Yeah. Do you also want to ask something? I assume. Yeah. In German. Okay. Yeah. I would like to ask something. Yeah. Then.
I think he can talk now. You just unmute yourself.
Oh, yeah, nice. I think now it works. Cool.
Yes.
Thank you.
Perfect.
Thank you so much,
Fantastic.
Davia.
Thanks a lot.
Thanks for that.
Yep, sure.
Yeah.
Cool.
Great.
Hi,
So
Tracy.
we have questions from the remote audience, Tracy. Yeah.
Yeah, hi, Renee. Great.
Hi, Tracy. Yeah, great to hear you and to see you too. I had a question on the slide, on the preceding slide. And there so as I understand it, there you have two lasers, right? And they are shifted. They have exactly this frequency difference of the two Siemens states, so like a few megahertz.
Right.
And they have a defined phase relationship.
Yep.
And so how do you generate them in the experiment? And how, yeah, I guess they must be co-propagating, not to pick up any phase from drifts or so. And
yeah, so it's actually one and the same laser because it's just a few megahertz. What we do is we send one laser through an AOM, through an acousto-optic modulator that we drive at two different frequencies. And so because we drive it at two different AOM frequencies separated by those few megahertz, then it has these two, then we generate sort of two co-propagating fields with a phase relationship.
Yeah, but there would be a little bit split off, right? There would be a small angle between them, but this wouldn't matter.
Right. So there's some small angle between them, but it's not, but we couple them directly into a fiber, and then that fiber gets them co-propagating. Yeah.
Got it.
So
so just a small efficiency loss. Okay, yeah. Great. Thanks.
You're welcome. Yeah, so right. So as I was saying, we can have a lot of control with this cavity method. And so I want to go ahead and show you then, that was a picture about entangling an ion and a photon. And let me show you what we've recently done, which is to generate ions entangled with photons at the university, which is where my labs are. But my colleague, Ben Lanyon, in another laboratory, which is at the Institute for Quantum Optics and Quantum Information. So this is another building that's about 500 meters away, linked by an optical fiber, actually a bundle of optical fibers, has in the past years built up a very similar experiment. So you can see that they look very, very similar. The one in the lower left is a little bit shinier, so the blades are actually gold coated, but the cavity is very similar. It's also 2 centimeters in length. And so this system is also capable of ion photon entanglement. And let me now go into a bit more detail about how we get this remote entanglement. And this is a very general statement, not just about ions, but about any kind of system where you have spin-photon entanglement. So what I've written down here in the upper left is a spin polarization entanglement, where you have spin up entangled with a horizontally polarized photon and spin down entangled with a vertically polarized photon. And that, of course, for us, that's these states D and D prime, but it could be any states. It could also be different polarization states as long as they're orthogonal. So let's now picture that we have two of those systems, like an atom and a photon here. And now we send the photons to a non-polarizing beam splitter. And that erases information about where the photons came from. So because the photons can exit either port of that beam splitter, then we detect the photons after the beam splitter, but we don't know which photon came from which atom. So we get some event of clicks at our detectors that register those two photons, and this projects us into an entangled state of the atoms. That is, by detecting the photons, in this case, this particular detection pattern leads to a anti-symmetric state, entangled state of the two spins, where either we have up down or down up, and there's a phase of pi between those two states. And so here I'm describing to you a detection scheme based on two photons. There's also ways that you can entangle remote spins based on a single photon detection scheme, but I won't go into that here. I'm happy to talk about it. So yeah, what I want to argue for you or describe to you here is that this is a very general protocol that we're going to apply for these trapped ions, but that people have used for other spin systems. And also, so it's heralded in that it requires the detection of the two photons. And if you happen, for example, to detect two photons with the same polarization, that's going to happen half the time. And what you do in those cases is you just move on and try again. So you're going to throw out half of your attempts, even if you have perfect detection, because you need to rely on the cases where you detect orthogonal polarizations. Okay, so what we're going to do is now we want to generate spin-photon entanglement in each of these two systems, send the photons over optical fiber, and see if we can entangle the ions remotely. But I want to point out that we need to make sure that the photons are indistinguishable from each other. And that's because of that beam splitter in the middle. So I told you that going through the beam splitter will erase information about where the photons came from, but that's only true if we have indistinguishability in all possible degrees of freedom. For example, we need to have them be temporally indistinguishable. So first here, we're just going to look at the detection events from both nodes, which we're calling A and B here. And you can see that from the axes on the two different y-axes, we have a lot more counts from node A than node B. And that's because it's a more efficient cavity, but also because the photons travel a bit less, travel a shorter distance there. But that doesn't actually matter. What matters is that when we scale the relative heights, the photons look pretty similar, the different temporal shapes, so these histograms about arrival times. So we say that, okay, temporally they look pretty indistinguishable. But what about spectrally? How do we tell about their how do we find out about their spectral or frequency indistinguishability? And this comes back to a fundamental quantum optics result called the Hong-Mandel effect, which tells us that if we have spectrally indistinguishable photons, or generally indistinguishable photons, that they will leave a beam splitter at the same port. So if we have two photons that are incident on a beam splitter that really are indistinguishable, they're never going to come out at opposite ports. So we're never going to get the kind of coincidences that I've illustrated here on opposite ports. So that was then the next thing that we looked at from these two remote systems before we tried to entangle them. We wanted to characterize their Hong-Mandel characteristics. And so what we looked at was two cases, one with orthogonally polarized photons, where we know that they're not indistinguishable because they're different in this polarization degree of freedom. And that was the case, that's the case plotted here in blue. And we compare the detection times between the arrivals of these photons. And we see that it's perfectly possible to get coincidences between two orthogonally polarized photons at 0 time delay. But if the photons have the same polarization, we can really generate identical photons, and that's where the coincidences are suppressed at 0 time delay. And that's what you see in this plot. So this is a plot that tells us that we have the necessary indistinguishability to go ahead and try and entangle these ions remotely. And then that required a lot of technical challenges that we've been working on for some years. Timing synchronization between the two labs, frequency synchronization. So how do we make sure that the cavities are really the same, generating photons at the same frequencies, and making sure that we stabilize the polarization of the link between the labs. And then we take the photons from the different labs, we send them to a polarizing beam splitter, and we perform what's called quantum state tomography. We measure the ions in different bases. That allows us to extract a joint density matrix from the ion-ion system. And then we can go ahead and calculate any entanglement measures that we want. Again, just to remind you, a single measurement is simply asking, is the ion bright or is the ion dark, using that fluorescence with that other excited state. So these are the key results from this experiment that I want to show you. This is a density matrix based on a single, looking at the target state that was a single one of the 4 maximally entangled Bell states, in particular the so-called psi minus state. Psi minus state, which is up down minus down up. And so we try to generate that state, and then we look at the density matrix that we do in fact generate between the two ions. We compare it with our target state. And we see that it has a fidelity with respect to that state of about 0.83. So there's a classical bound that says you wouldn't be able to do better classically than 0.5. Perfect fidelity would be 1. And so we see from the error bars that, within the uncertainties, we're well above that classical bound, even though we're not quite perfect for some reasons that we understand pretty well at this point. So this is, again, a sort of a density matrix of the two ions that shows us that they are in fact entangled. That was one state based on kind of one set of click events from these detectors. We can also generate a so-called psi plus state, and this is a symmetric state, up, down, plus, down, up, and it also has a very high fidelity. So these are two different density matrices now that we can extract and analyze for these remote ion entangled states. I want to just kind of let you know that we're looking at photons we window the region of the photons that we detect. We look at photons that arrive just within 1 microsecond of each other, and that allows us to get a higher entanglement fidelity, although it is at the cost of the overall number of entanglement events. So we have a trade-off between the fidelity and the number of entanglement events, and we can sort of choose to have more events but a lower fidelity if we want. But no matter what the window is that we look in, we still always generate a non-classical fidelity for entangling these ions.
Tracy, is there a reason that the psi plus state has a little bit higher fidelity than the psi minus state, or it's just within the statistical error bounds, you would say?
Yeah, as far as we can tell, it's within the statistical error bar.
Okay.
So there are some differences in the detectors that in the detectors that you're using, because 2 of them are superconducting nanowire detectors and 2 of them are avalanche photodiodes.
Oh.
But when we analyze it all, it seems to be within the error.
Okay.
Yeah, so that's the kind of picture where we've entangled 2 remote nodes. We're hoping that paper will come out on the archive in the next few weeks. So we've been writing up for a while, working on theory analysis of Nicolas Sanguard and his group. We've also been working on a 3rd node in my group, which is a fiber-based cavity. I won't have time to talk about it today, but I want to just tell you that we've kind of used a system with optical fibers near an ion to test electric field noise models and ion traps. And in that experiment that we did last year, we controlled the distance between a dielectric mirror and an ion in order to characterize the heating rate of the ion as a function of distance. So just a kind of quick summary of some other work that we've done. And broadly, what we're interested in with these kind of miniaturized ion trap cavity systems, we'd like to generate scalable systems so that we can, link together not just 2 or 3 systems in the future, but many systems that are easier to build. But something that's going to be crucial in that effort is understanding surface-related electric field noise, because trying to build sort of smaller, more compact, scalable systems comes with its own set of technology challenges. And we've been working again on kind of some different kind of scalable architectures. One of them is shown in this picture here. But I do want to briefly now tell you about the second aspect that we're working on, just in a couple of minutes. And this is really along the lines of the work that Renee is doing as well. So back to this idea of quantum optomechanics and the question about observing superposition
Tracy,
and entanglement.
before you change topics, one question about the scalability here. So I mean, if I understand correctly, then you always use some Bell state analyzer on the photons, right, to establish the entanglement between the, and then these Bell state analyzers actually have a kind of success probability of 1/2, because you can only detect psi plus or psi minus, right?
Right. Yep.
And then yeah, when one wants to use something like that for like multi-node networks, then this will pose like serious concerns about scalability. I just wanted to hear your opinion on whether there are other potential schemes that people are thinking about, or like whether this is a fundamental limitation that we'll have to live with, or
yeah, so the point that you're making is right. This kind of Bell state analyzer is only ever going to get you two of 4 states. Yeah. So I guess I think that's not the biggest problem that people are worrying about. So there are other schemes where you would have direct transmission, for example. And it's interesting to compare those schemes for particular platforms. Generally, I think that this scheme is going to be more robust to channel, to sort of corruption in the channel than direct transmission. And I would guess that, I think that that you can get around issues with the 50% aspect on the Bell state detection by multiplexing at your nodes. Yeah, so I guess that the best way to answer that maybe would be that I think in other groups, in groups that are really focusing on kind of the theory of how to scale up these networks, people are more and more doing simulations that are very much based on actual systems that have been realized. And I think that those kind of simulations are really going to give us insight into where the losses are when we scale up these systems.
Okay, I have one more question. Thank you for very interesting results. So to real scale quantum networks, we need a memory, and that means an efficient memory. So that we need not only to store state, but also to have high enough probability to extract the state of our, let's say, ion after the successful Bell state measurement. So can you say a few words about the storage time? So how long can you keep this ion after to wait for successful base state measurement, and how efficiently can you measure it afterwards?
Yeah, absolutely. So for the ions that we're using, calcium-40, the lifetime of this is limited to about a second. However, you could easily, so for us, that's a long time, a second, in terms of these measurements. So we don't really mind. But if you really, if the memory time starts to limit you, you could switch to using other ion species. With the ytterbium-171, people have shown memory times now of more than an hour. So that's the sort of spectrum where you can get, memory times of something like an hour for trapped ions. And the readout is very high fidelity. So reading out, this is over 99%.
So does it mean that if I want to read out, then I with 99% may make successfully, or make a correct readout?
Yes. Mm-hmm.
Oh, correct readout. Okay, thank you.
Yeah. Yeah, but both. Sorry, I mean that there's a both that you right that there's a you get an answer and then it's the correct answer. So ions are great memories. The hesitation about maybe ions is that they're slower than other memories and they're not as parallelizable as other memories. So you may want in the future to use things like, say, rare earth ions in crystals. So rare earth ion doped crystals for these kind of parallel aspects of temporal and spatial and spectral multiplexing. Yeah, so just to kind of tell you briefly about this other line of work that we're doing, also with ion traps and cavities, we're interested in looking at the motion of levitated systems where we suspend a particle in, could be many different kinds of traps, and we're using electromagnetic traps here. And so what's the role of quantum interfaces when we focus on the motion of particles and think about making it quantum mechanical? The idea is that light can allow us to have quantum in the future, quantum control of these systems. And what's exciting about these systems right now is that they're just now reaching the quantum regime. But access to quantum states has been limited by the strength of this light motion interaction. And so these are results from both Marcus Aspelmeyer's group in Vienna and Lucas Novotny's group in Zurich, where they've now been able to cool the motion of particles that are levitated, that are held up against gravity to the motional ground state. And so this is kind of now right at the entering this quantum regime for this motion of these particles. What we're interested in doing in my group is introducing a new interface, not only between the particle and light, but now also between the particle and an ion's electronic state. And we'd like to do that as a route to producing quantum states of motion. And so the idea is that we're building a system where we think that the cavity will couple to the motion of the particle, but the cavity can also couple to the electronic state of an ion, as I've described to you in most of this talk. And we'd like to combine those two systems in a way that allows us to generate non-classical states of motion. So we've been focusing on the nuts and bolts of getting there in the past few years. We've shown that we can load and cool nanoparticles in an ion trap. We work at ultra high vacuum with these particles. So this is a picture of a trapped oscillating particle at below 10 to the minus 10 torr. We've shown last year that we can now cool these particles in an ion trap to about 10 millikelvin. So this is still now not at the level of the quantum limit. This is maybe something like 10,000 photons in the motion of those particles. But we've learned a lot about cooling them, and we understand how the agreement or how to compare theory and our experimental results with cooling down these particles and trying to bring them nearer to their ground state. And more recently, the most recent work that we've done has been to take insights from ions, and in particular from a method of self-interference for detection and feedback cooling of ions that we've used now to implement what we're describing as a self-homodine method for detection of these particles. And what I'm just showing you here in this plot, looking at a power spectral density of detection motion of particles, is that this is a way that, building on these insights from ions, we can really get a much more sensitive detection for the motion of these particles in our ion traps. And that, we believe will allow us to get perhaps even all the way down to the ground state working under ultra high vacuum with this system. And so finally, I also told you that these were not just stories about ion traps, which is how we trap these charged particles, but also about working with cavities. And so this is something that we're also constructing in my group, optical cavities to which we want to now couple the motion of these particles and eventually also couple trapped ions. And we're heading, we'd like to head towards the quantum regime. I haven't described to you any results that are in the quantum regime yet. And I've just told you that, there's only a few groups now worldwide who are working in the quantum regime, but it's an exciting time because we're really at that threshold where having, seen ground state cooling in both the Aspelmeyer and the Novotny groups, the field is now interested in preparing non-classical states, and in the end, moving towards large quantum delocalization and in macroscopic quantum superpositions. So to wrap things up, we started this question about connecting different kinds of quantum systems. I showed you how we can connect ions in different cavities, but I also showed you how we're coupling nanoparticles to light and how we're hoping to bring that system as well, a much larger system, into the quantum regime. I've described to you that our quantum interfaces between atoms, photons, and phonons allow us to build links between disparate experimental platforms. Somehow this doesn't, here we go. Trapped ions are, and then trapped ions are one of the leading candidates for nodes of a future quantum network. I've described to you that recent demonstration of ion entanglement over 510 meters of optical fiber between two buildings. And I've also motivated optical cavities as an interface to the motion of macroscopic objects such as nanoparticles, which can provide a route to preparing novel quantum states. So with that, let me wrap up and show you the people who've been working very hard on this project. Thanks.
Thank you very much, Tracy, for such a fantastic talk, super pedagogical, super clear. And of course, congratulations on the amazing job you guys been doing. This is really cool, really interesting. As usual, do we have questions? Especially from the more junior guys, if there are questions around.
There's one. Cool.
Can I go first, René?
Of course, Philip.
You mentioned in the end that you're also building your own cavities, and I'm curious on what kind of methods you use to build your cavities.
Yeah, so we use a couple of different methods. So let me go back a few. So this design is something that we've been building. I mean, this is an example of quite a macroscopic cavity where the mirrors are separated again by something like a few centimeters. And so then the challenge here ends up being about constructing a system. So we work with first with mirror coating companies to get a very low loss, highly reflective dielectric mirror stack that corresponds to our target wavelength. And then we have the mirrors that we want, and the task is to assemble a system that's very physically stable, that's very robust to vibration isolation, but nevertheless gives us a tunable range so that we can tune the length of the cavity over a full wavelength, essentially, so that we can kind of access all vary modes. So this is an example of a kind of thing that we're building. But I also mentioned these fiber cavity setups, and this is a system where we work together. We collaborate with Jakob Reichel's group in Paris to ablate the surface of optical fibers, then have those coated with a dielectric stack, and then we work on positioning the optical fibers parallel or facing one another to create a cavity mode.
René, do you have a question?
Yeah,
I can see you. Yeah, please go ahead.
I'm cool. So one more mini comment. I think there's another group who just entered the quantum regime, but I guess this is the group of Marin. They had a paper in April 2022, so just a very short time ago. I think
yes, that's also right. Exactly. Yeah, so that's not on these slides yet, but I should have mentioned that as well.
Yeah. Cool. But my question would be, it's a little bit just touching this very nice paper which you have written on this heating. If you bring an ion close to a dielectric surface, and we discussed this in our team, and it was great. We liked it a lot. And my question would now be: so if I now move away from the ion, and let's say I have a nanoparticle, and this nanoparticle, I can now make it such that it has a zero net charge, but it still might have some charge patches on it. And now let's assume that I have this nanoparticle at a short distance from your mirror. So I mean, you look here at let's say a few hundred microns. Could you, like from the hip, shoot an estimation if there would still be some detectable heating, or would this be negligible if I have no net charge on the particle?
So we haven't done the estimation, and I think the answer is that we should do it. You know, it's something we've thought about as well, and I don't know the answer without working through the math on it.
Okay.
Yeah, because I guess in the end, it's that you have, there's this oscillation frequency of the particle in its trap, whether that's an ion trap or an optical trap. So you have this oscillation frequency, that's the one you care about. And the question is, is there, given the charge that you're describing, which could be the charge of the particle itself or particular charged patches, do you have enough dissipation in your material that you're generating that sufficient noise? And yeah, I think the right way to do it is just to do the calculation.
Yeah. Okay, cool. Yeah, sounds good. And do you estimate, because I mean, there's this argument, it's I mean, I never went through the math, but I think Markus Aspermeyer once brought it up that the nanoparticles are much more sensitive to noise than ions. And the argument is kind of that there's the ground state wave function, the width of it scales with 1 over the square root of the mass. And now if you go for big mass, the width of the ground state wave function gets smaller, and then you're also more susceptible to noise, to small displacement noise. And this was the hand wavy argument. Can you comment on this? Is this idea correct or?
Yeah, I mean, I think as a hand wavy argument, it makes sense. I guess what we saw from this paper, this was a paper where we took a specific geometry for our trap and modeled it based on this fluctuation dissipation theorem to calculate the predicted noise. And I guess it seems to me like these kind of trap geometries are or the sort of geometry of any particular experimental system is so complex that I don't trust these kind of intuitive arguments.
Yes, exactly.
All
yeah. Okay. Yeah. So okay. I got it. Super. Thanks.
This was a super clear talk, and we asked several questions during the talk. This is a fantastic line of research. This is very exciting to see the advances of what you guys are doing. It's really amazing. Then, if there are no further questions, we thank the speaker again, and thank you so much, Tracy.
Yeah, really great. Thanks a lot.
You're welcome. Thank you so much for the invitation. It's great to be here.